Hello, this is Eric from UNC Charlotte, and this is part 6 of our crash course on C++. If you haven't seen the previous part, you can find link to them in the doobly-doo. As a reminder, this crash course is not meant to make you the perfect, ideal C++ programmer. It's mostly meant to catch you up on common issues that you could run into whenever you're writing C++. And the topic of today is to figure out how to debug C++ codes when they go wrong. In my experience, there are two types of bugs that you'll run into in C++. One of them is purely algorithmic type of mistakes. You'll find those things with standard debuggers. And debugging those things is the same thing in C++ as it is in other programming languages. The type of issues I want to talk about today are the type of issues that are more specific to C++, and they tend to be memory-related issues. And I'll show how one particular tool, in my opinion, knocks it out of the park and help you find all kinds of errors very early on in your programming process. Here I have some code that is written, and we'll see that whenever we run it, that code dies. All right. So whenever we run this application, it causes an error called segmentation fault. And essentially, segmentation fault is an error that happens whenever you are writing or reading to a piece of the virtual memory of your process that has not been allocated. If we're looking at what the code is actually doing, it declares a variable, A, and then it takes the address of A, and it adds some value to it so that it points in some random places in memory. And whenever we are going to try to write at this memory location, it is very likely that this offset that we added is going to make that pointer point in some random place of memory that's probably not allocated and on which we don't have permissions to write, and so it's not going to work. And that's the reason why we get segmentation fault. Now, segmentation fault can be really, really hard to debug. In my experience, the best way to debug all kinds of memory errors is to run your program through a memory debugger. There are different ones that are available depending on the operating system you're running on. I believe that people on Windows run Purify. On Linux, I believe the best one out there, or at least it's free and very easy to use, is called Valgrind. And the way you use Valgrind is you simply run your regular program through Valgrind by doing something like this. And whenever you run it, Valgrind is going to add some of its own information that will tell you why that are really the logs of Valgrind itself. And it can tell you that there was an invalid write of size 4 that happened inside the main function. Now, that does not give us a whole lot of information. The reason why it doesn't is because whenever we compile this program, we did not compile this program with debugging information. We can actually add debugging information by adding a -g parameter to the compiler. And I've done that here by using the makefile to add the -g parameter that adds debugging. And now if we run this one through Valgrind, we are going to learn a little bit more about why the things crashed. And you can see that now Valgrind can tell us a little bit more about the error that we have. It still can tell us that there is an invalid write of size 4, but now it can also tell us where it happened. So it tells us that it happened in this file on line 9, and I suppose this is line 9. Yes, this is line 9. So you see, Valgrind gives you a lot of information. The first thing that it tells you that it's an invalid write of size 4. That makes sense because we're trying to write an integer. It's a 32-bit integer, so they are 5 bytes large. That's why it's an invalid write of size 4. You can see the issues was a write, it was not a read. If I was trying to use the value of *p to do something else, I would have an invalid read of size 4. And it can also tell us where in the code that error occurred. Now, Valgrind can also tell us something a little bit more. It can tell us that the address that we try to use, it can usually gives us some information about it. And here the information that it gives us is that that address is not on the stack, it has not been memory allocated, and it has not been freed recently. So that tells us that this pointer is essentially completely in a random place in memory, and that's what it's telling us, and that makes sense. We added some random value to it. Most likely it's nowhere in particular in memory. So that's what Valgrind tells you. It will usually tell you when there is something fishy happening with memory. It will tell you what type of operation caused the error. It will tell you at what line of your program the error occurred. And it will tell you some context about the address that was accessed and that should not have been accessed. So now you could go back to your code and try to read it and understand why that error happened. Let's look at a different case. So here, what we have a very simple program. It's allocating some memory, and it's allocating it by calling new. And in modern C++, you should never, probably almost never, call new directly. But there are cases where you run into code that do that, or there are cases where you're going to want to do that anyway. And here what's happening is that we allocate memory, but we don't free it. And let's see what Valgrind is going to say about this. You see, whenever you run Valgrind, it will tell you that at the time where the application exited, there was memory that was still in use. It will tell you that there were 48 bytes that were in one block of memory that are still in use, and it tags them as definitely lost. And it's 48 bytes because we are allocating integers, and integers are 4 bytes each. We allocated 12 of them, and so that's why it's 48 bytes. Valgrind can tell us a little bit more. It tells you actually here that you can add some additional parameters to get some more details on the leaked memory. So let's see what it does when we do that. Here it will tell you something that's interesting as well. It will tell you that, okay, so we lost 48 bytes in one block, and it will tell you where that memory has been allocated. It will tell you that that memory has been allocated in function main in this file on line 5. So you can go back and see where that memory was allocated, and that can help you pinpoint which piece of code should have been responsible for deallocating this memory, and then trying to investigate why it was or wasn't deallocated. Some other issues that can happen in C++ are linked to jumps. Here what we do is that we declare an integer and we make a test on it. Then we use that integer to compute some other value, and we make a test on that. Let's see what Valgrind thinks of that. Here Valgrind tells us that there is a lot of things that are happening. In particular, it tells us that there is a conditional jump that depends on an uninitialized value, and that it happens line 7. And that's line 7. And indeed, Valgrind is right. Here we are making a test on variable a, but variable a has not been initialized. In C++, primary types and variables of primary types, when you declare them, are not initialized. In some languages, all integers are initialized with 0. This is not the case in C++. In C++, whenever you declare a variable of a primary type, you have to initialize its value with something. Otherwise, the application is going to pick whatever is in memory at the time where this variable was declared. So here a has some random value, and that's why it tells you that you have an initialized jump. It will say that again a little bit later on line 13, which would be this one. And also whenever you try to print those values, it will also tell you that there is something fishy happening because the values themselves were not initialized, and you try to displays them, and in the inner code of how you display that, there will probably be some jumps or something like this. So Valgrind can also show you that you're using memory that has not been initialized. Now, the way Valgrind is written, it will only warn you that you use a value that's uninitialized whenever you try to make a jump or some kind of a test based on it. If you're just trying to add things, it's not going to warn you. It's really when you're going to use them. And see how that happens, right? A is uninitialized because it's not been initialized. And because you use A in this expression, that means that the value of this expression is also, it also depends on an initialized value. And so Valgrind can tell you that the value of the value of B, it depends on an initialized value. So it can not only keep track of the direct value that's not initialized, but it can also cascade the property that the value is not initialized from one variable to the next. And this is a common source of error in C++. Let's look at our next case. So one of the most common error in, I suppose, most programming languages are essentially off by one errors. It's the kind of errors where maybe you're writing a little bit too much after the end of an array or something of that sort. If you run that piece of code, it's actually going to work. But if you actually run it in Valgrind, it will show you that there is something off going on. The Valgrind is going to tell you that there is an invalid write of size 4 that happens on line 9. I suppose that's this one. And indeed, we are writing past the piece of memory that we can write, because whenever that code was written, we went up to values of I that are less than 20, but the array itself is only initialized for 10 entries, and so eventually this line is going to write past the end of the array. And there are two things I think that are interesting here to notice. The first one is that whenever we run the program, it actually does not show any error message. And the reason for that are complicated, but it's mostly because whenever you allocate memory in general in any operating system, usually the system does not provision exactly the memory that you request. It usually round that up to the next block, maybe the next 4K block or the next 1 megabyte block or something like this. So whenever you try to access memory that is after the value of P that you requested, that piece of memory actually exists, and it has been reserved by the operating system. It has not been reserved for the use for P, but it has been reserved to the operating system. And that's why you do not get an error of segmentation fault on a code like this. That being said, whenever you run that code in Valgrind, Valgrind keeps track of memory allocation in a way that is a little bit more fine-grained than the operating system, and Valgrind can tell you that there is something going on that line that is wrong. And it can even tell you something a little bit more interesting than that. It will tell you that the address that you're accessing is 0 byte after your block of size 40. So it actually tells you that the error that you're getting, the error that it's reporting, is because you're trying to write directly after the block that you allocated. And sometimes that can hint you at what the problem actually is. Notice that Valgrind also suppressed some of these errors. There were more errors happening. It tells you there were 10 more errors that were happening, but because they all looked the same, it actually just didn't display them. And there are parameters that you can pass to Valgrind that are going to let Valgrind know that you want to see all of them. And you can go ahead and do that. It's not going to be very interesting here. It's just going to report the same error 10 more times. Another common error that happens in C++ is the use after delete error. And let's look at what it does. Let's run that code normally first. So here what we have is that we allocate some integer and we're going to write to it and we're going to print the value, and then you're going to free that pointer that was allocated. And despite we freed it, we are going to keep on writing on it, and we're going to print it again, and we're going to try to delete it again. Let's see at what happens whenever you try to run this code. The interesting thing is that obviously the first printout should use the right value of 12, but the second printout happens as well. You can see that you deleted the A variable, but when you try to write at the address of A, that appears to have worked. It shouldn't work, there is a bug, but the operating system cannot tell that there is a bug. And the reason why it cannot tell that there is a bug is because the way memory allocation works is that once a page has been allocated, it is not going to be pulled back by the operating system in most circumstances. That's why you do not get segmentation fault here. The error that you get happens whenever you try to delete A again. And it's because that's the time where the language library notices that you're trying to delete something that has already been deleted, and that clearly means that something wrong happened. But it's interesting to see that the error that happened first has not been reported. And this is, in my experience, one of the biggest problems that we have when people use row pointers and do errors whenever they allocate and deallocate memory, is that they're going to have old pointers dangling around that they're going to write to. And this can cause havoc because the memory could have been reused by some other external data structure. So if you write on a random piece of memory, you can potentially change the state of some random data structure in the code. Let's see what Valgrind tells us about this. Whenever we run that code, it actually can tell us about this. First, it will tell us that there is an invalid write of size 4 that happens on line 13. That's line 13, so it detects the error as soon as it happens. And it will tell us a little bit more about that. It will tell us that this address, it's within a block of it's within a block of memory that used to be allocated, but that has been freed. And it will tell you where that block of memory has been freed. It's been freed here on line 11. That's what it tells you. And not only it can tell you where that block has been freed, it can also tell you where that block was allocated. It was allocated on line 5. It was allocated here. Valgrind will also report the error that happens on line 15 for the read. And finally, when you're double deleting A, it will also tell you a similar piece of information about the fact that it's a double delete. It will tell you where the data has been deleted and where that data had been allocated. So, in summary, what I'm trying to tell you is that Valgrind is a very good tool to detect and help you correct codes that do incorrect things with memory. And one of the reasons why I think Valgrind is so useful is because it helps you detecting errors not at the time where they trigger something in the library or something in the operating system that causes the application to crash. Valgrind in many cases can report the first time in the execution of your program where the execution went wrong. It can tell you the first time where the code did some access to memory that it was not supposed to do. And on top of being able to point to you to the first error that it detected, it can tell you lots of things about the context of this particular memory access. And that usually means that you'll be able to backtrack your code and be able to identify why this happened. If you only wait for segmentation fault to occur for you to go back and look at what happened, the problem is that you could have a pointer that has been wreaking havoc in your memory for a long time in the execution of your program. And by the time segmentation fault occur, you might be witnessing the consequences of a previous error that was not reported by your operating system. And fortunately, Valgrind can help you detect error earlier in that process, because the closer to the actual error that you get, the report that you're getting from Valgrind is usually going to be much closer to the initial error than a report of segmentation fault or something like this is going to be. And Valgrind is going to help you detect all kinds of error. It's going to help you detect double freeze. It's going to help you detect buffer overflow, buffer underflows, dangling pointers. It will be able to tell you whether it's a buffer underflow, a buffer overflow, or a dangling pointer. It will be able to tell you about double freeze. It will be able to tell you about uninitialized memories and things of that sort. So what I personally do is that whenever I write code as part of the test that I do of my applications, I tend to always run them through Valgrind. And it is extremely rare that Valgrind gives you false positive. In almost all cases, if Valgrind tells you there is something fishy here, there is something fishy here, and you should look into it. All right, that's all I have for you today. I hope I convinced you that you should be using some kind of a memory debugger on your application. Personally, I use Valgrind. The other ones, I think Valgrind is about as good as it gets, and so that's what I use. All right, goodbye.